Hello learners, I welcome you all to this video program on conical projections at this level, that is BSc General, third semester core course on general cartography. We are studying three types of conical projections, that is conical projections with one standard parallel, conical projections with two standard parallel, and then Bonne's projections only. At higher levels you will study more complex form of conical projections. And in the last program we studied the graphical construction of conical projection, that is simple conical projection with one standard parallel, and also learned its properties. In this video program we will study about the graphical construction of conical projection with two standard parallel. We will also learn about its properties, and then we will learn how to construct graphically the Bonne's projection, which is a very special type of conical projection, and we'll also learn about its properties. And then after viewing this program you will know how to differentiate between these projections, and you will also know its applicability. So let's start with conical projections with two standard parallels. Suppose you get a question. This is also a practical paper actually. It is a core course. One is theory paper, that is general cartography, and in after studying the theory you get these types of problems, and then you have to draw the projections graphically. So the question is, construct the graticule of simple conical projection with two standard parallels on a scale 1:25 million for an area extending between 20 degree north to 80 degree north latitude. This is the latitudinal extent given in the question, and 10 degree west to 70 degree east longitudes, and the interval for between the longitudes and latitudes is given as 10 degrees. So this is the scale is given in the form of representative fraction, and you must have studied about representative fraction in previous blocks related to cartography. So if it is given as 1:25 million, then it means that 1 unit on map represents 25 million units on the ground. So we know that radius of earth is 4,000 miles, and 1 mile is equals to 63,360 inches. So if we convert miles into inches, then we get approximately 250 million inches as the radius of earth. So what would be the radius of reduced earth? Like I told you, what is first for those who missed the previous program, first what is projection? Projection is the method by which we transform the graticules of latitudes and longitude from three-dimensional spheroidal earth to a plain piece of paper or two-dimensional system. So in a way we try to flatten the earth on a piece of paper on any two-dimensional surface. So in this process definitely all the properties of earth like homolographic or equal area, or the shape of the globe, or true bearing or direction would not be preserved. So all the projections are not having are not true with respect to all these properties, but some of the properties are preserved in some of the projections, and so its applicability varies. As I told you, like 250 million inches radius of earth. So if the scale is given as 25 million, then 25 million inches represents 1 inch on the map. So 250 million inches would definitely represent 10 inches on a map. So we get the radius of reduced earth as 10 inches. I have explained this in this slide. Like radius of reduced earth is 10 inches. Now we draw a circle with 10 inches radii, as you can see in this figure. This is actually an example of conical projection with two standard parallel. What is standard parallel? Basically, when you studied about simple conical projection with one standard parallel, then you came to know that standard parallel is the parallel along which the scale is correct, And so in this case it is two standard parallel, so the scale would be correct along two parallels in this case. So it will be definitely an improvement over the previous conical projection. And when the latitudinal extent is given like 20 degree north to 80 degree north, then it's better. Like if we take 30 degree north latitude and 70 degree north latitude as the standard parallel, then almost 2/3 of the latitudinal extent would be covered in this projection. We select 30 degree and 70 degree as the standard parallel, and you see the longitudinal extent is given as 10 degree west to 70 degree east. So the central meridian would be the 30 degree east longitude. You can see in this figure. Later I'll tell you how to construct this. After drawing the circle of 10 inches radii, we draw an angle ROB equal to 10 degrees, because this is needed in the previous projection also. While studying conical projection with one standard parallel, we did this like this would be the distance between the parallels and along the central meridian RB, this RB distance, this arc RB distance. And with this arc we construct a semicircle at the center with center O. This RB arc we take and we construct a semicircle like this, and we draw two angles which represents the standard parallels, like angle A1OB equal to 30 degree north latitude and angle A2OB equal to 70 degree north latitude, which we have taken as standard parallels. Now this semicircle which we have drawn at this place, it will meet A1O at X and line A2O at A. It is meeting at these points X and A. Now from X we draw a perpendicular to the line OP, so that it is intersecting the line OP at point Y. You can see this. And from A we draw a perpendicular to line OP again, which meets the line OP at B. Now these two distances XY and AB will become the distances between the meridians along 30 degree north standard parallel and 70 degree north standard parallel. Now come to the right side of this figure. We have drawn a central meridian or a vertical line VBY. Now from VBY we take this RB distance, which is the intersection points of the parallels on the central meridian, and we mark the latitudinal extent, we entire 20 degree, 30 degree north, 40 degree, we mark with this RB distance. This entire thing is this RB distance. Okay. Now from 30 degree is our standard parallel. From 30 degree and from 70 degree we draw lines AB and XY, which is equal to AB and XY of this semicircle part which we have just now drawn. We have got these distances. Now after drawing these, we connect these 2 points and we extend this line to intersect the central meridian at point B. Now V becomes the vertex of the cone. After getting all these points, now we come to the next figure, this one, and we draw a line again VBY as the central meridian. And from central meridian we take this distance Y and V. V and Y. This distance we are taking from in the central meridian to mark the points. This pole is projected over V, and this is the Y. Y is the point of intersection of the 30 degree north standard parallel, and from here with the help of this VY radius we draw an arc representing the 30 degree north latitude or parallel, 30 degree parallel, which is the standard parallel. And from this point we again take this RB distance and mark the other parallels, like we extend it to this 20 degree north latitude. This entire parallel is 20 degree north latitude, this is 30, and then we mark other points also with this RB distance, as we have done in here also. We mark other points like this. This is our latitudinal extent, from 20 degree to 80 degree north latitude. And taking V as the center, we draw arcs of circles, concentric circles representing all the parallels. And from this is the standard parallel, and from Y we take the distance, this XY distance, and mark the intersections of different longitudes along this standard parallel. This is XY distance, then this is also XY distance, this is also XY distance. So in this way we mark all the points of intersections of the different meridians from this standard parallel, that is 30 degree north latitude. And similarly we do the same for 70 degree north latitude, taking this distance AB, the distance between the meridians along 70 degree north latitude. That is, this distance is AB distance, this is AB distance, this is AB distance. And after getting the points, we join these two points, the point we have got on the 70 degree north latitude with the 30 degree north latitude. These points we join with a straight line and we extend it to the latitude, entire latitudinal extent, and we connect it with the pole. So in this way we draw all the other meridians also. So this is conical projection with two standard parallel, because we have taken the intersection points, all the meridians at the standard parallel, two standard parallels. So it is definitely an improvement over the previous conical projection with one standard parallel. So coming on to the properties of conical projection with two standard parallels, you see parallels are arcs of concentric circles. We have drawn it from the same point, and the meridians are straight lines radiating from the center. You can see meridians are all radiating from the center. There are two parallels which are drawn true to scale, and all meridians are drawn true to scale. The distances between the standard parallels are shorter than their actual distances, while beyond them they are longer than their actual distances. So as I told you, this is an improvement over the conical projection with one standard parallel, and it is suitable for comparatively larger areas of mid-latitudes like that of Canada, Russia. In case of conical projection with one standard parallel, very small latitudinal extent was correct, that is along the standard parallel. But since in this projection there are two standard parallels, so a greater latitudinal extent is more accurately drawn. It is representing the true Earth in this case. And because the distortion is reduced, that's why I told you that the distortion is reduced between the two standard parallels. Now there is another projection which we will study at this level, which is Bonne's projection, and it is a special case of conical projection, and it was named after the French cartographer Rigobert Bonne, who designed this projection. When you learn the graphical construction of this projection, you will know that in this projection all the parallels are made true to the scale. Suppose you get a question like construct the graticule of Bonne's projection when RF is 1:320 million and the interval is 10 degree for an area lying between 35 degree north to 75 degree north latitude, and the longitudinal extent is given as 0 to 60 degree east longitude. Radius of Earth is 6,400 in kilometers. When we convert this kilometers into centimeters, we get 640 million centimeters. Now if the RF is given as 320 million units, then 320 million units is represented by 1 unit on map. Then 640 million units would be represented by 2 centimeters. Like 640 million centimeters divided by 320 million centimeters would be 2 centimeters. So we have got the radius of reduced Earth as 2 centimeters. Now latitudinal extent is 35 to 75 degree north. So central parallel or the standard parallel is selected as 55 degree north latitude, although in this case we make all the parallels true to scale. Now longitudinal extent is 0 to 60 degree east, so the central meridian is selected to be 30 degree east longitude. Now come to the construction part quickly. We are drawing a circle with radius 2 centimeter, which is the radius of reduced Earth, and then we draw all the angles of latitude, like we had 35 to 75 degree. So we draw angle A1OB equal to 35 degree, angle A2B equal to 45 degree. Similarly, angle AOB equal to 55 degree. Now this is angle A3 OB equal to 65 degree and angle A4 OB equal to 75 degrees. Now we again draw, since interval in this question is also 10 degrees, so we draw an angle ROB equal to 10 degrees, and this is the arc of the RB. With the arc RB we draw a semicircle from the center O. At this point we are drawing, and which is intersecting all the parallels at some points. You are saying I have only marked the intersection point for the standard parallel, which is, otherwise you can see it is intersecting all the other lines also at these points. And from those lines where it is intersecting, we are drawing again the perpendicular and meet this line OP from the respective intersection points of the semicircle along these lines A1O, A2O, and then AO, A3O, A4O. Now these distances we get, again these are distances between the meridians along all the respective parallels. Now we draw a straight central meridian, we draw it like this, and this is the radius of the standard parallel. AP is the radius of the standard parallel. With this distance we mark AP. This is the polar projection, and this is the line of the standard parallel, intersection point of the standard parallel along the central meridian. Now after getting this intersection point, we draw a curve, we draw an arc taking radii PA, and this marks the standard parallel. After this we take this again RB distance and we mark all the other points as intersections along the central meridian for all the different parallels. The latitudinal extent is 35 degree north to 75 degree north, so we are drawing all the intersection points with RB, same RB distance we are drawing. After that we draw an arc taking the radii at different intersections, and which is the arc of all the parallels. We draw it like this, and after drawing we mark the intersections of different meridional distance between the respective parallels, like these distances along like 35 degree north latitude we are taking this distance, then along 55 degree north latitude we are taking xy distance. So we mark all the intersection points of meridians along different parallels, and since this distance is different for all the different parallels, so it can't be drawn with a straight line, we join it with smooth curves. Now coming on to properties of this projection, all the parallels are concentric curves. However, their curvature depends on the selected standard parallel. All the meridians are drawn as smooth curves. The scale is true along all the parallels, and all of them are drawn true to the scale. Scale is also correct along the central meridian, but away from central meridian there is distortion, and this is also an equal area projection, like each quadrangle on the map represents an equal area on the globe. So what are the uses of this projection? Since it is an equal area projection, it is suitable for maps of Europe, North America, Australia, and it is used for topographical maps of countries like Netherlands, Belgium, Switzerland, etc. For Africa, we have another projection, which is the sinusoidal projection. Learners, what we have learned in this video program, we have studied the graphical construction of conical projection with two standard parallel, and we have learned about its properties. You have also studied the graphical construction of Bonne's projection, which is a very good projection since it is equal area or homolographic projection. This is a practical paper, so even if you don't get to do these in your study centers, you can watch these programs and very well understand. And if in case you have any doubt, you can always contact us at satyaraj@ignou.ac.in. So keep watching, learners, and get back to us with your feedbacks and suggestions. Thank you.